Hi everyone. Today we're going to talk about a topic related to quadratic equation, especially solving, called complex numbers. We'll talk more in a second about what that means. But suppose we wanted to solve this equation: x squared plus 1 equals 0. To do this, you can use whatever solving method you want. But since I see this one lone square term, I'm going to work to get it by itself. So x squared is -1. Then again, because I have a perfect square on one side of the equation, I can deal with that by taking a square root. Square root property applies and brings that plus or minus along with it. But you probably spot an issue here, which is that we've got the square root of -1. If you punch the square root of -1 into a calculator, you're going to get some kind of error message or something about it being undefined, because this is not a real number. In real number terms, you can't take the square root of a negative because multiplying a negative by another negative is always negative by a negative is always positive. So because of, oh, I'm so sorry. There you go, x. So this is not a real number. Or again, you might get a message like it being undefined from a calculator or something. But if you think about it, this kind of thing could come up a lot in what we've been talking about, right? Think about the quadratic formula. That solves any quadratic equation you want. Well, if b squared minus 4ac, so if this part is negative, then we'd be in the same kind of situation, right? So this can come up a lot. This turns out matters for some applications and things. So to be able to deal with this, sort of extend things by defining what we call an imaginary unit, imaginary because it's not a real number, and unit because it acts like one. We write it as usually like a script lowercase I to be the square root of -1. Specifically so that we can deal with this sort of thing. So x then is plus or minus the square root of -1, which means it's plus or minus I. Okay, well, that gives us some kind of added ability to deal with quadratic equations where this might come up. So this quadratic x squared plus 4x plus 5, and the equals 0 part is important, whether we're going to try to factor or use quadratic formula. Thinking about factoring real quick, factors of 5 are 5 and 1. They have the same sign, which means I'm not going to be able to get them to add to 4. So this isn't going to factor in a nice way. So I'm going to jump to the quadratic formula. Negative b squared, 4a is 1, c, and 2 times a. Just write that times 1 in there. Okay. And as usual, I'll just start cleaning that up. -4 plus or minus 16 minus 20 under the square root over 2. Which is the square root of -4. Now that we have this idea of an imaginary number, I, notice that if I take 2i times 2i, I get 4i squared. So in a lot of ways, we can treat I just like we would a variable, right? So work with it the same way you would x. So multiplying those, I multiply 2 and 2, and I multiply I and I. If I is the square root of -1, then I squared would be -1. So -4. So back over here, the square root of -4 is the same thing as 2i. Then again, the plus or minus really means that there are two things there, one from adding and one from subtracting. So we can reduce -4 over 2 is 2, and 2i divided by 2 would be I. So these are our two solutions, one 2 plus I and the other 2 minus I, in what we call the standard form for a complex number. It's called a complex number because it has a real part and an imaginary part. So this is just the real number 2, and then we're adding the imaginary number I to it. When you have real and imaginary, we call those complex numbers. And the usual thing is to write them as a plus b times I. So in other words, the real part comes first. So real part and then imaginary part is the usual way to do that. So now we can solve, we said the other day that using the quadratic formula, we can solve any quadratic. Now we can really solve any quadratic in the sense of actually finding complex solutions to it, right? Whereas if we're limited to real numbers, we might get here and say, oh, this thing doesn't work, so I guess this has no solutions. It's true that it has no real solutions, but it does still have complex solutions, and there they are. So in practical terms, the only thing that's new really is that we've got this sort of extra layer to dealing with simplifying square roots. So let's look at that for a second. Simplifying square roots. What we do here is not really any different than places that we've done this before. If I wanted to simplify something like the square root of -20, I can almost treat these like they're separate pieces. Just think about the square root of 20 for a second. 20 is not a perfect square, but 20 does factor into 2 times 10, and 10 factors into 2 times 5, which means that the square root of 20 is the square root of 2 times 2 times 5. And because it's a square root, anything that shows up twice under the radical can come out of the radical. So the square root of 20 is 2 and leaves behind the square root 2 times the square root of 5 left behind underneath. So that's how that part would work. The square root of -1 is I. So the square root of -20 then is 2 times square root of 5 times I. So like I said, it's just kind of adding an extra layer to what we can do and what we already know about simplifying a square root like that. Another one real quick. Let's throw a negative outside there. -50 maybe. This comes out as I. Color coding is going to get confusing here. Okay, so an I from that negative under the radical, square root of 50. And then again, 50 is not a perfect square, but 50 is 2 times 25, and 25 is 5 times 5, which means the square root of 50 we can break into 5 times the square root of 2. So this would be -5 square root 2 times I. Okay, so that's the kind of thing that we may need to do with something like this in solving a quadratic, right? This one, the square root of -4, happened to be a perfect square, so we just got 2i. But as you've seen, hopefully in other places now in homework and in example problems, we could end up with things like this as well that we need to simplify while dealing with the quadratic formula calculation. One other thing while we're here is to just take a quick look at how we do arithmetic with complex numbers. And I'm just going to do this by some examples. So addition. Like I said a minute ago, that for the most part, we can treat I no differently than we would treat an X or any other variable. And that's true for arithmetic for the most part as well. So if we want to add two complex numbers, right? So I know this looks like four things, but this is one complex number that has a real and imaginary part. This is another complex number. To add them together, all we do is add the like terms. So those are the real parts. These are the imaginary parts. So this turns into 1 plus 2. I'm just using the parentheses for grouping for emphasis. 1 plus 2 and 3i minus 5i. Right, so I'm really just combining like terms. 1 plus 2 is 3. 3i minus 5i would be negative 2i. And that's it. So again, the highlight real parts, imaginary parts, and then you just combine like you would a variable. The same thing would be true for subtraction. You would just subtract instead. So if you're subtracting, just be careful to, a negative here would get distributed as usual. For multiplication, again, it's going to be very similar to the way we multiply 4 minus I maybe. Multiply or expand binomials. So complex numbers have two parts. There's a real component and an imaginary component. But that means when we multiply these two things, we're multiplying, sort of four possibilities together. So basically what we're going to do is just a FOIL-like expansion, or, if you do the little box thingy, or, however you would do this expansion. So 2 times 4 is 8. 2 times negative I would be minus 2I. And I'll rearrange stuff at the end. 3i times 4 would be 12i. And then 3i times negative I would be minus 3i squared. Okay, and there are like terms that I can combine right there. So 8 plus 10i. And then the one other thing that we can do is that for complex numbers, the, what's the word? Convention, the usual thing, is that we don't leave powers of I unreduced because of what I is and how it works. We can always reduce those down. In particular here, I squared is -1 because I is the square root of -1. So really this is 8 plus 10i plus 3, and then we have another like term to combine. 8 plus 3 is 11 plus 10i. So that's how multiplication works. Again, initially very much like multiplying two binomials. So we do a binomial expansion or a FOIL type expansion with this extra little bit of a catch to it, that because of what I is and how it works, we can reduce powers of I down. Okay, and that leaves division. 1 plus 2i over 2 minus 3i. Okay, division, as usual, is the place where things get a little bit weird. Because if you think about what this is asking, you know, we usually think of division as like equal sharing, right? Well, if that 3i wasn't there, I can imagine dividing each of these things by 2, right? Just splitting them in half. I don't really know what it would mean to divide by 3i though. So the way we handle division with complex numbers is to rewrite it so that we don't have to divide by a complex number. The way we make that happen is to multiply by this, which is called the conjugate. This is one of those things that the reason why we do what we're about to do will become clear as we do it. So multiply by this conjugate thing. Now, if I multiply by that in the denominator, because I don't want to change anything, I'm going to do it in the numerator also. So we're going to do multiplication like we just did, only in the top and bottom here. So let's start with the top. 1 times 2, so 2. 1 times 3i, 2i times 2, and then 2i times 3i. Should be 6i squared. We'll clean that up in a minute. Then do the same thing in the denominator. 2 times 2, 2 times 3i, 2 times negative 3i, 3i times negative 3i, 9 minus 9i squared. And any of that, like pause the video, take a second, do the expansion yourself, just to make sure you're okay with where we got all that. Now I'm going to start combining stuff. 3i and 4i would be 7. 6i and minus 6i would be 0. This is the reason that we use this thing, because those go away now. And the other thing that happens is that, again, I squared is the same thing as negative 1. So the reason we chose to multiply by the complex conjugate is that now the stuff in the denominator becomes 4 plus 9, so 13. The numerator 2 minus 6, so negative 4 plus 7i. Now it's still a complex number, but I know how to make some sense out of dividing by 13, whereas dividing by this complex number that has, you know, an imaginary part and a real part, this I don't really know how to deal with. This is something that tracks a little bit better with what we know about how division works. And again, it gives us a way to write it as a single complex number with a real part plus some imaginary part. So that's how division works for complex numbers. There are some more examples in my notes in Blackboard. Again, my filled in copy of the notes is up there, so you can take a look at a couple of more. The complex arithmetic stuff in particular, just do a few examples and kind of get a feel for it, but that's not going to be a major point of emphasis moving forward. It's just a thing that we want to kind of take a look at. The thing that's going to come up more frequently would be this kind of thing, where it shows up in the context of solving a quadratic, and maybe you need to be able to do some square root reductions like that. Okay, well, thank you. Hope that's helpful. Please let me know if you have questions.